The microprocessor works by executing a program of instructions. Creating a program is similar in concept to programming in BASIC, C, or any other high-level computer language. Each type of microprocessor has its own instruction set, which is the set of commands that it was designed to recognize and obey. Microprocessor instructions are very elemental and specific, and it usually takes more than one to accomplish what a single high-level language instruction would. Many microprocessor instructions simply move the data from one place to another within the computer. Others perform mathematical or logic operations. Still another group of instructions control program flow, such as jumping forward or backward in the program. Each instruction in the instruction set is assigned its own unique operation code, which is typically 8 bits long and referred to as the opcode. The CPU uses this 8-bit number to identify the instruction. All microprocessors have at least one accumulator, which is a data holding register in the CPU. The accumulator acts as a staging area for data. It is common for data coming to the CPU to go first to the accumulator, where it can be operated on. Similarly, most data leaving the CPU exits the accumulator. Mathematical operations usually store the results in the accumulator. Many of the instructions involve the accumulator in one way or another. A machine language program is a list of instructions in opcode form for the microprocessor to follow. Before the program can be executed, it must first be loaded sequentially into memory. The opcode for the first instruction is loaded at the first address location. The opcode for the second instruction is loaded next in line, and so on. The diagram shows a section of memory with a short program loaded in. The program listing includes the address, opcode, mnemonic, and a brief explanation. A mnemonic is an English abbreviation of an instruction. A program listing using only mnemonics is called assembly language. Note that the opcode is shown in hexadecimal as a shorthand for binary. If you need a reminder of this, see the presentation on the extra resources section of Blackboard entitled Hexadecimal Shorthand for Binary. The program in diagram B directs the CPU to get 1 byte of data from input port 01, add 1 to it, which is the increment command, and send the result to output port 2. Before execution can start, the address of the first instruction must be loaded into the program counter. The program counter is a special address storage register that the CPU uses to keep track of where it is in the program, much like a bookmark. The program counter always holds the address of the next instruction to be executed. Once the microprocessor is activated, execution of the program is completely automatic. The execution process is a series of fetch-execute cycles, whereby the processor first fetches the instruction from memory and then executes it. The following are the specific steps the microprocessor would go through to execute the program of Figure 2.4b. The microprocessor fetches the first instruction from memory. It knows where to find the instruction because its address is in the program counter. Once in the CPU, the opcode is decoded to see which instruction it is. Then the proper hardware is activated to execute this instruction. In the example program, the first instruction, in01, is 2 bytes long. The first byte of the instruction is the opcode telling the CPU to input data from a port. The second byte is the instruction which tells the CPU which port to read from. Execution of this instruction causes data from input port 01 to travel along the data bus to the accumulator. Also, the program counter advances to 02, the address of the next instruction. Execution of the first instruction is now complete. The next fetch execute cycle starts, this time fetching the instruction from address 02. The new instruction, INRA, is increment the accumulator. So the accumulator is sent to the ALU to be incremented, add 1, and the result put back in the accumulator. The program counter advances to 03, which is the address of the next instruction. The next fetch execute cycle starts, this time fetching the instruction from address 03. The instruction out02 is executed, causing the accumulator data to be sent to output port 02. Program counter is incremented to 05. The next fetch execute cycle starts, this time fetching the instruction from address 05. The instruction halt is executed, which causes the microprocessor to cease operating and go into wait mode. This ends the presentation dealing with sections 2.1 and 2.2, namely the introduction to microprocessor system hardware and operations or software. The next section deals with how microprocessors interface with other equipment.